Welcome to our webinar entitled Integrating Senses, How AI is Learning to See, Hear, and Interact. From this webinar, you will understand the significance, challenges, and state-of-the-art solutions associated with developing AI systems that can seamlessly integrate the visual, auditory, and textual data in real time. You'll find out about the techniques developed by the Qualcomm AI research team and the tools that we are open sourcing for developers. The webinar today is brought to you by Qualcomm and is a continuation of our webinar series about AI. My name is Armina Stepan, and I am here with the tech marketing team at Qualcomm. I'll be the moderator today. Before we get started, I'd like to show you how the webinar platform works. At the bottom of your screen, there are multiple application widgets you can use, including a widget to download today's presentation. All the widgets are resizable and movable. The slides advance automatically throughout the event. At this time, we recommend that you disable your computer's pop-up blockers. This will allow the slides to advance automatically throughout the event. You can participate in the Q&A session by asking questions at any time during the webinar. Just type your question into the Q&A widget and then click on the Submit button. We'll answer questions after the presentation. Also, if you're having any technical problems, please type your issue into the Q&A widget as well, and we'll be glad to help. I would like to now introduce our presenter for today, Roland Memisevich. He is the Senior Director of Engineering at Qualcomm Canada. Roland, please take it away.
Okay, thank you everybody for being here today. I'm going to be talking about AI models that can in real time interact with you through camera and microphone, so that can see and hear you and have an understanding of the world around them. This is a topic that has been very dear to me for a long time, and so I'm very happy to be talking to you about this today. The agenda, just real quick, for the next 45 minutes or so is I'm going to introduce an architecture that has emerged pretty much as a blueprint for these types of model that allows a model to stream, say, pixels or audio samples in real time and then deliver responses at the same time. Then I'm going to talk about how to train those models end to end by having the appropriate data sets that show the model behavior in response to the inputs it's supposed to see and allow it to train from that. I'm going to talk a little bit about some architectural aspects that are specific to the application that I'm going to present as a showcase, which is a fitness coaching application. And finally, talk about some more research efforts that have had a long tradition, but that are really coming back now in the community about instilling more common sense in those models so that they work better in the end. Qualcomm has a very strong footing in generative AI models, and generative AI has become very popular recently. The kind of work that is happening here is ranging from obviously voice systems. So Qualcomm is building hardware that powers edge devices, and so it's a leader in edge AI. And so voice applications, speech recognition, and these kind of things have always been an important research direction for the research group here. More recently, large language models have come on the map, and so now you can run pretty sizable language models on your phone, thanks to some of the more advanced research efforts that have happened. There's a lot of video rendering and these kind of things. So all the kind of things that you can imagine should happen on your phone or on other edge devices, maybe even cars and IoT devices and so on. What I'm going to talk about today most fittingly covers the point on the bottom here, which is agents, building live real-time agents that can interact with you in real time. The outcome of these research efforts over recent years is very visible through applications like this. So you can now have models that run on your phone that are, say, conditioned on an image, and then you can have a Q&A dialogue about that image without having to turn on your Wi-Fi. So there are models now that can easily run on your battery-powered device and deliver value that way. And so what I'll talk about today is a little bit of an advance of this vision of having a multimodal system running on an edge device towards where it might land sometime in the future. there is a lot of buzz these days around embodied AI and humanoids that might one day roam our homes and so on. And we believe that along the path to such a future has various steps along the way. And one of those steps I'm going to cover today. So from left to right, right now we are able to run LLMs on edge devices. We're going to probably keep pushing the abilities of these models in multimodal scenarios. So where you have an image and you ask the model, can you please tell me how many calories are on this plate here that I just took a picture of, and these kind of things. The focus today is going to be the light blue box in the middle, which is basically expanding from that ability to look at an image and do Q&A on that, to having a real-time system that uses the camera stream and knows how to behave sensibly in response to that camera stream. And if you continue that idea further, then at some point you might end up with embodied AI models, so robots that have a camera and a microphone, and you can talk to them and so on. But it's worth noting that if you look across the board at current embodied AI efforts like that, if you look at the humanoids out there, if you walk up to them and look into their face or wave at them, they usually don't know what to do with that because they don't have a real live understanding of what's happening around them. In academic terms, this is sometimes called situated. They're not really immersed in the situation that they're in. They're trained to solve manipulation tasks on a space in front of them, but they don't really know where they are, why they are here, what the humans around them mean really to them, how they should behave towards them, and so on and so forth. And so that's the research that we believe can be addressed right now, even a step ahead of humanoids, with multimodal streaming AI models, which I'll talk about today. This whole story is an edge story, right? So because of privacy and latency requirements, even though you could offload some workloads to the cloud, the pixels and the audio samples will always arise at the edge. So there's always a substantial amount of processing happening at the edge. And for sheer scalability, there are so many edge devices out there, so many phones and other devices. There's a strong focus now to get these capabilities right onto that edge device as much as possible. So in a nutshell, what this light blue box in the middle represents is use cases like these. So imagine smart home, smart mirrors that can see that you're there, and then they can behave accordingly, knowing that you're looking at them right now, and provide value that way. Similarly for phones, and then a little bit into the future, maybe robots will be getting much better thanks to having some situated sensing capabilities that these models are currently lacking. The sort of showcase application along which I'm going to present a lot of the research results is going to be fitness coaching. We noticed a couple of years ago that fitness coaching is a very nice research playground to study those real-time situated AI models. For once, because it provides real value. It is not easy to get your hands on a personal trainer. It costs money and effort to get into a routine with that. So it would be immensely valuable if you had a coach in your pocket and you could just put up your phone and ask it to watch you while you're performing exercises, and then improve yourself or get just cheered on as you're doing it. But on top of that, fitness coaching is a beautiful application that requires an AI model to really be there with you in real time and know what to say in the right moment in response to a visual input stream that it is subjected to and that is constantly changing as it's watching. So we have built fitness type use cases for several years. What you see on the right of this slide here is an example model that we looked at several years ago that is composed of various boxes here, various components. So you have a camera stream gets processed by a vision model. There's an orchestrator that decides what to do with that output of that vision model, maybe hand it on to some kind of language model. The language model decides what to do or what to say next. The orchestrator turns that into text-to-speech, and then the front end displays it, et cetera, et cetera. what has happened in recent years, and so that's really the core thesis of this work and the main topic today, is that a lot of these component-wise models have been replaced by just a single neural net that ends up working much better and to behave much more gracefully when things don't go exactly as you anticipated them while you were building out this system. So this, in some sense, continues a tradition that has arguably started something like 15 years ago, where people discovered that if you take a speech recognition pipeline and replace it by a neural net, it just works much better. So we can just train a neural net end-to-end on samples in, text out, and then have the model do all the step-by-step processing, dealing with phonemes and so on and so forth. And it works really well. That idea then encouraged a lot of researchers to try to expand that, and very visibly and famously, Ilya Sutskever and others at University of Toronto tried that for object recognition and trained the model on ImageNet, and then again took a pretty complex computer vision pipeline, replaced it with a neural net that was just trained end-to-end on the task at hand, that does feature extraction and all of those things. And it works just really well. And so that tradition has continued on and on and on over the years. Next step around that time was machine translation, and there were many more steps along the way. So what I'll talk about in this research work here is, in some sense, taking this progression and imagining how it will look if you think it all the way to the end. So if you push this all the way to the end, what you will have is a neural network that has to be autoregressive, or might call it recurrent in some way. It has to be a streaming processor of some sort. And it needs to be subjected to some kind of perceptual input. So that's the input stream on the left. And in response to whatever the perception gives it, it has to behave in some way. And so what we are envisioning here, and it's not just us, it's several folks in the community that care about these type of models, is it going to be possible to take this vision and materialize it just with one single end-to-end trained neural net? So that's the purpose here. We want to have a neural net that is a stream processor and that knows what to do and when, just because of having been trained on appropriate data. Just a few words on that streaming architecture that will be required to do that. First of all, we want to do this multimodal. So we want to have a model that ingests, in our case, it's going to be pixels, but similar efforts are underway in doing this for audio and other modalities. So we want to have a neural net that ingests pixels in real time. So they're going to be streamed into the model, and that then decides what to do. There's a blueprint of an architecture that has emerged for doing that, and that model looks like this picture here. The main executive control is handled by an autoregressive language model. Language models are already autoregressive in this way. They produce one token at a time. And as such, they are already stream processors in some sense. So they're functionally equivalent to a recurrent net. Even though they're not recurrent, they in some sense cheat by keeping around history. But for most of these applications, it doesn't matter. So the model does step-by-step generation of tokens in response to some kind of visual input. The visual input is usually a convnet. The language model and the convnet or vision transformer, whatever input module you have, are usually pre-trained, and then there's some kind of adapter that mediates between the two. And then the job of that autoregressive language model is to generate tokens or take actions. So there can be a separate action module that is triggered by the language model output, or we can even interpret the tokens that the language model itself produces as actions that are then maybe passed on to a robot driver or whatever the task at hand is. But one thing that's worth noting, despite the really blooming field here and taking this blueprint, so a language model controlled perception system, despite all of this work, the vast majority of it is not yet streaming enabled. And there are just a few things one needs to consider in order to make it a streaming model. I will talk about them in a little while. So the models that currently exist and are very popular in the community are models like Lava, earlier ones like Flamingo, introduced by DeepMind, and various others. They usually differ in the way that they ingest that visual information. It can be just represented in placeholder tokens that take the place of textual tokens and instead take on the job of representing visual information coming from an attached coordinate or so. They can also have a cross-intention mechanism that I'm going to get back to also in a little while, where while the model generates tokens one at a time, it not only self-attends to the past language in its context window, but it also cross-attends to that input modality, for example, that vision feature. What's striking about all of these models is they are a really big step forward, mostly thanks to using pre-trained language. But the applications that are covered currently by these models are still somewhat constrained to tasks like captioning, visual question answering. In a nutshell, these models that are popular in the community right now are image conditioned language generation models foremost. And if you think about the vision of having a stream processor where you have visual input coming at a certain rate and output being generated by the model at a certain rate in real time, you need to go one step further than that. And so the technical steps that we need to take, that's what's shown on the bottom, are we need to be able to freely interleave vision frames with language tokens. So instead of having a visual input, then generating text, please tell me the amount of calories on the picture that I took from my plate. The model has to be continuously ingesting visual information and continuously responding and decide when to pay attention to vision, when to pay attention to what to say next, and so on. Secondly, the model has to be able to trade off compute that it does on the perception side with compute it does to generate tokens. And that means that as a model designer, you have to be careful in trading off frame rates, for example. At which frame do you want to watch the camera stream? At which frame rate can you generate tokens? How many tokens do you need for the application? And so how do you trade these things off against each other? And then third, and that's the most, by far most important point, I would say, is you need training data. So if you want to have a model that is no longer just taking an image and answering questions about it, but that is freely interleaved, dealing with a camera stream and behaves in response to what it sees, we need to have some kind of data where the appropriate behavior of the model is rolled out into a sequence of video frames aligned with a sequence of tokens in this case, so that the model can be trained end-to-end to do that. And that is really the goal of what we're up to here. There's some work emerging in this direction. So we have been looking at this. There are various other works. One somewhat visible one is Video LLM Online by Chen et al. And all of these kind of approaches now depend on having a training data set that it allows us to do essentially behavior cloning in the kind of model. So I'll talk now a little bit about a specific data set effort that we have been involved in for quite some time now, and what the data landscape looks like generally. So just like these models are now emerging, so there is architectures that interleaved process visual information and tokens. There's also a little landscape of data sets emerging. So the most visible ones, most important ones are, I believe, the ones that I show on the slide here. There's a data set called HoloAssist, which is a first-person data set that is supposed to enable models to understand a video feed or a sensor feed more broadly coming in from an AR device, and then allow the model to understand what's appropriate to say or what the person is doing right now for the purpose of walking somebody, for example, through the task of repairing a watch or fixing something and these kind of things. So basically manipulation, guiding somebody through manipulation tasks. The second one, the one that's shown in the middle of the screen here, is called WTAG. Can foundation models watch, talk, and guide you step by step to make a cake? It's a very simple testbed, a beautiful testbed application, again through an AR device, where the goal of the model is to walk you through preparing a recipe step by step by watching you, seeing what you've done so far, what you should do next, and so on. And then there's ours, which we introduced and open source recently, which we call QEVD, Qualcomm Exercise Video Dataset. That one is a third-person dataset where a user is in front of a camera, for example, by placing their phone next to them. And the camera watches the user doing various exercises, many different kinds of exercises, and understands what kind of mistakes they're making, how what they're doing relates to how they've been doing in the past, how they should improve their form, whether they did it, and so on and so forth. So that data set, I alluded to that in the beginning, has been cooking for quite some time. That was also the data set based upon which we built our first component-wise applications before really going into the end-to-end vision for this. It's pretty substantial. It has many hundreds of hours of video. Many participants who helped us collect this data across many, many exercises. And it has basically two parts: short video clips that allow you to ground the model's perception in important concepts, like seeing that you're not going deep enough into your push-up, that you are not keeping your legs close enough while you're doing your squat, etc., etc. And then there's a long-form data set. That's the piece that's relevant for end-to-end training of the whole model, that contains full-fledged fitness sessions that a user does, usually across a bunch of exercises. And that fitness session is aligned with coaching information from a good coach who knows what to say at what time to cheer up the user, give them feedback, help them improve, etc., etc. Just in a nutshell, some statistics on this data. So there are short clips for grounding, the key perceptual concepts, and then there are long-range videos for end-to-end training. The long-range videos, there's a few hundred of them, but each of them contains multiple exercises, giving us in total a few thousand individual exercise sessions that users are doing. It can be used both for training, and then there's a test set that can be used to evaluate the model's ability to perform this kind of task after having been trained end-to-end. Along with these data sets, there come annotations. So the most important one for the long-range videos is just what you should say at which point in time, aligned with the frames of the video. But then there's additional surrogate data that allows the model to become better at understanding those key concepts and becoming a better vision model to understand the video stream. And those are taking the forms of questions and feedbacks. Just a quick picture to show you what the data looks like when you download the zip file and open it. So you have video frames for the long videos here shown on the left, and alongside that you have comments from the model that tells the user when they're doing well, and that also tells the user what they should change. So it's not just positive feedback, it's also understanding mistakes, and then also understanding whether the user did or didn't fix the mistake that the coach has called out. And then on the right, you see a few excerpts from the short form videos, so the clips where people are doing exercises with various form and mistakes. And so the form can be really good, or it can be subtle mistakes, or they can push really hard. They can go really push themselves into going deep into their squats, or they can just keep them shallow, and so on and so forth. And as you understand those concepts from the live video stream, you can sensibly respond to encouraging users and calling out their mistakes, and so on and so forth. One more statistics slide in comparison to existing data sets. So as I said, there is an emerging little community and research effort around interactive assistance of this form. And I mentioned those three data sets now that are publicly available, and people are starting to play with them: WTAG, HoloAssist, and our QEVD. There's a ton of data sets that has been around for years now, has been evolving on general video understanding problems. This is early ones about action recognition and so on, also even some fitness specific ones, and then ones that are a step closer to end-to-end assistance, but they are still lacking the aligned feedback data. So basically the behavioral cloning data that is needed to have a model really trained end-to-end on this task. So those are the models you see on the bottom, the data sets you see on the bottom. Okay, I'm going to talk now about one technical aspect of the particular model that we created as a baseline, but also now as a demo for this fitness application. Hopefully it's going to elucidate some of the challenges that come along with domain-specific models. So this is just going to be a short venture into some specific of this model in terms of its visual capabilities. And after that, I'm going to talk about some really interesting grounding aspects of improving grounding for these models, and then show you some results. So on the left, you see the architecture blueprint that I mentioned before that is now moved more and more towards being streaming enabled, thanks to these end-to-end streaming datasets. On the right, you see a blow-up of the model to show you more detail. So in this type of baseline that we created for this model, we are using cross-attention. So it's a little bit like Flamingo. In that the model, while it's generating tokens, attends to the visual input via cross-attention, rather than putting the visual information in the forms of token embeddings into the context window and then just using the language model's existing self-attention machinery to attend to visual information. So in this case, it's cross-attention. And a specific aspect of this model, the way in which we handle the need to know when to speak and when to watch, is handled by the model itself. So the model needs to decide whether it should keep its eyes open and watch for visual information, or whether it can quickly deliver feedback and then go back to watching. So the way this is solved in this particular model is that the model can either say, next, please give me the next frame, I'll keep watching, or it can output a feedback token, after which it's going to produce a bunch of tokens that represent feedback that the model wants to give to the user. After which it's going to go back into next and say, please keep feeding me visual information. This is one way to solve it. For us, it allowed us to create a model that is efficient and leaves that decision-making to the language model, so it can be trained end-to-end on doing that. And it works nicely, but it's obviously not the only way. And so now there's a real need to do more architecture exploration, specifically in thinking about how to get these models to run efficiently on device and so on. How to handle this need of freely interleaving visual and token information in this type of architecture. A second wrinkle I want to mention quickly before moving on to a more researchy topic is the need to understand motion in this application. So when we first started to venture into this type of application, so we wanted to have a model understand what the user is doing, we realized quickly that if you take a 2D convolutional network, or equivalently a VIT or whatever the 2D image model might be, the model misses a lot of information about what the user is doing, because a lot of the information, specifically when you're doing exercising, is encoded in motion patterns. And so that's the way pixels evolve over time. And so you need to have a temporal component in your vision model to understand not just edges and Gabor-like features and higher level features in an image, but also temporal, spatio-temporal features in a video. So we quickly realized that one way to get to such a model is to use a 3D convnet. So that is a convnet that has 2D convolutions in the image domain and 1D convolutions in addition in the temporal domain. And that quickly learns to encode motion patterns, behaviors, and so on. But the problem with this 3D convnet, if you want to deploy it at the edge in real time, is that if you do it naively, you're going to wind up with a lot of compute, because if you naively process a video stream across time, and at time t+1, the next frame comes in, then you would just be redoing all the computations up to time t. And there is no need for that because the model already processed the path, essentially. In order to make this more real-time and edge-friendly, we came up with an implementation, essentially, that is using what we call steppable convolutions. It's a well-known trick to use in similar streaming scenarios, where instead of reprocessing the whole visual input every time a new frame comes in, the model just keeps state at time t or a few steps before, depending on how far the temporal convolution reaches, and then updates its state to equivalently just take into consideration the latest frame to update its state and then provide you the features at the output. A second required trick there is to train the model so it doesn't learn to cheat by looking into the future. So recall that the training data is videos paired with labels or coaching advice by the model. And if you would do this naively and use a 3D ConvNet, then the model would be encouraged to make use of whatever future information that the video stream might contain to provide a response right now. But if you have a real human or a real coach or a real person behaving in the real world, of course, you cannot look into the future. You have to make use of whatever information you've seen so far. And so because of that, we're also using causal convolutions. So we have temporal convolutions that only reach backwards and that don't reach forwards. Together, this gives us a model that is a 3D ConvNet that makes use of steppable and causal convolutions, and that can then easily be run efficiently in real time on a phone, for example. We have this model, we open source this model. It's available under this address here, which is also in the materials, I think, that is coming along with this presentation. It's in github.com/quick/sense. So we called this sense, the model SenseNet, and it was trained and shown to work well, not just on fitness coaching, but also gesture control and various other applications that require a model to understand motion patterns that a human is showing in front of the camera. Okay, so now for a research subtlety before I talk about some results. So we have a language model as the backbone for this type of scenario. And a language model makes sense because it, at the end of the day, enables a model to respond in response to a video stream. So the vast majority of applications that are now emerging and that are relevant for this kind of behavior is the model needs to know what to say in response to an input stream. And so language models are well suited for that. There is a more subtle aspect about language models and language in the first place that we make use to provide better grounding for the model. And that is, language is a beautiful way to encode very complex information that you can tease out of a perceptual input stream and then use that as a way to train the model to understand that information. Several folks, including ourselves, have studied this, if you want to call it, misuse of language for the purpose of instilling common sense in the model for many years. Here's a somewhat dated effort from like 7-8 years ago. We had a data set called something something that shows videos with very subtle behavior patterns. And as it is, that data set comes with a hierarchical label structure. So it comes in classes, but it also comes in captions, and it comes in various degrees of sophistication for those captions. And so we decided around 2017, hey, let's take this data set and see whether training on more and more complex labels allows the model to become a better and better feature extractor for downstream tasks. So using language as a way to instill some degree of common sense in the model rather than a use case in itself. So what we did is took a two-stream vision encoder, had a classification task that you see on the left, and then we said, okay, let's also attach a decoder language model to that system and feed the model labels that talk about increasing degrees of complexities that you can infer from those videos, since that's something data set provides for these various degrees of complexity. And so then what happens if we take that model and just use it as a feature extractor to apply it to a different task. In this case, the different task was a home cooking task, and we could see how the model does on this home cooking task. And then, as we were hoping, if you go increasingly complex on your labels that you use for pre-training the model, the better the model works as a feature extractor for a task that is not the same. It's maybe related, but it's not the same as the pre-training task. So it's basically a way to misuse language as an encoding for subtle features, such that some degree of common sense emerges in the features of the model as it's trying to solve a downstream task. We took this idea much further in some more recent work that we called LRR, look, remember, reason, where now the language model is not an LSTM like it was back then, and the model is much larger, and it's a pre-trained language model, and so on. And there we showed that if you apply a similar idea to various visual recognition tasks that are very, very sophisticated and subtle, this kind of extra information, the extra information you can provide a model about stuff in the visual scene is very, very helpful, and in fact gives us state-of-the-art results on some very difficult reasoning, including causal reasoning tasks that involve vision. So the form that this information takes is ranging from object identification, re-identification through multiple frames, tracking objects in the video, and so on and so forth. And so in this case, the model is simply trained to watch, potentially in a simple task, image conditioning. So to look at the image or look at the video, derive a bunch of information like bounding box positions of hands, positions of objects, where do these objects reappear in another image, and so on, and then solve the actual downstream task. So this is basically a form of chain of thought reasoning. So using, again, misusing quote unquote language to perform chains of thought that are not directly linked to the task at hand, but that can benefit the task at hand because you just understand more details about the visual scene while you're trying to solve this problem. So that works very well. It comes with one, or actually two drawbacks. One is that if you perform such a chain of thought on the visual information, you wind up with a much larger number of tokens that you have to process on your device than what you want to. And so that obviously has some efficiency implications. If you really just care about the answer to the task, it's cumbersome to also produce all kinds of thoughts in the middle. And the other is that it can still be brittle. So the model can start generating chains of thought that may not be completely correct at every point in time. And when it then, in the end of that, generates the actual answer for the task, it might trip up because of some mistake that it did along the way. To address both of these problems, we came up with a way to have the model know about those chains of thought, but not making them explicit in tokens. And the way we are doing that, and that's something that has also emerged as almost like a standard little approach now that people are using, is by distilling that extra information into the model at training time. So what's happening in practice is we're training the model on watching the perceptual input, responding if appropriate, but with a certain probability during training. Think of it like dropout noise, maybe with 25% probability or 75% probability, prompt the model to provide an answer to a surrogate task. Surrogate task being, where is object XY at this point in time? Or where do you think it will be next? And so on. And when the model is trained on this hybrid set of tasks now, the actual downstream task and also the surrogate tasks via stochastic probing, it does much better on the actual downstream task than it would by solving the downstream task directly. It loses a little bit as compared to chain of thought in the particular set of experiments that we have done. But it comes with a huge benefit, which is inference speed is much, much better. So, and that is significant. So instead of having to think through the problem at inference time, the model's features have emerged to understand the aspects of the scene that are relevant to solving the downstream task. And they encode that information sufficiently to do almost as well as training directly with the chains of thought represented as tokens. But since those tokens don't have to be generated, the model can shoot out an answer and still be informed by that surrogate information. We call this stochastic probing. At the same time, there was work that did something similar, for example, for chain of thought reasoning, distilling chain of thoughts, basically, an approach called distilling step by step. And there are now various other papers that do something similar. It works very well for visual information, and that's really what we care about in this scenario. Okay, so if you take this model, 3D ConvNet, that is inference friendly because it does steppable causal convolutions, attached to a pre-trained language model like Llama, and trained on end-to-end sequences to provide coaching advice, then we get a real-time model that can now ingest the video feed and respond to the user while being informed about all the little mistakes, all the little things that the user is doing well in the moment, and then based upon that, take a decision about what to say at what point in time. I'm going to show a quick video here of a model that we are now demoing, where I encourage you to look at the bottom response. That's the latest model. So this is really hot off the press. It's like cooking as I'm talking about it. And so here you see a user working out, and the model not only decides what to say while the user is working out, but also makes a decision when it should speak up, when it's worth saying something. And those occasions are typically cases like here, where the user is doing okay, but maybe makes some little mistakes or just doesn't put enough energy, bending their knees enough or jumping. And so here you see another example. Maybe you are running this in the lab. And so remember, this is a neural net. It's a language model that is just trained to directly take pixels and speak. It started to learn to count because some of this probing information is counts as well. The counting is not perfect, but it's at this point roughly correct, which is kind of interesting if you think about what is involved on the feature level to let the model monitor periods in the activities that you undertake, and then appropriately give you numbers, like you have done 10 reps so far and so on. Here you see another example, cheering the user for how well they're doing. The model also sees when somebody walks away, because this kind of ability is just coming through with the training data. And then, for example, prompts the user to come back, or suggesting to defer to a later day, etc. So again, this is a model that is just a neural net. 3D ConvNet feeds visual information to a language model. Language model decides when to watch and when to talk. And the model is trained end-to-end on this QEVD data set that I mentioned before. And that's pretty much all there is about this model. Here's a few more qualitative, just a few more quantitative examples before I'm going to wrap up. The left panels here show the comparison to what a model trained this way says to what a model says that is just prompted. So there are lots of video LLMs out there now. Most of them are video conditioned, as I mentioned in the beginning. And evidently, if they haven't been trained on this grounding data, where they really understand how exactly did you move your arm as you're trying to do this jumping jack, etc., then there's no way that it can provide common sense responses to how you're doing. And so it's just a lack of grounding that shines through here. On the bottom left, you see ground truths and what the model says, a few more qualitative examples. And on the right, again, a comparison to what the model says in response to a specific video and how that compares to, for example, prompting or fine-tuning an off-the-shelf video model without paying attention to the domain-specific aspects here. Lastly, there is, as this field is evolving and data sets are coming up and streaming models are being explored that can run on device and so on, there's also an emerging need to come up with metrics to study how well the models are performing and so on. These are the metrics that we use, and they're also kind of along the lines of what is emerging in the community. It's still early in this field. You can use the standard language-based metrics, and they show similar behaviors in that a small improvement in the metric can come along with a big improvement in actually watching the model perform. There are two aspects that have to be covered. So you need to know whether what the model says is sensible. As in, did the model call out a mistake you did in your squat by keeping your knees too far apart? And second, the model has to be able to determine when is it appropriate to give that kind of advice. So if some time has passed, and you've spoken about something else, it may no longer make sense to call out this mistake that is now somewhere in the past. And if it's the right moment, then you should quickly call it out and then see if the user corrects themselves and then decide to continue talking about this mistake if there are still issues, or switch to cheering them up again, etc., etc. So there is the what to say and the when to speak aspects that we're trying to cover with these metrics and others to similar things. And so there are various ways to do that. You can ask a language model to compare to the ground truths on your validation data. You can use like an F-score that you window in some way to make sure responses come in the right moment. And you can do various other things. And so this is an emerging field that hopefully is going to allow us and others to provide some quantitative estimates in lieu of human feedback, which you can always do, of course. Okay, I'm going to wrap up after just mentioning one more project that we are working on that is related to this, and that is pushing a little bit further to the right on that initial picture towards humanoids. Once you have a streaming language model that ingests a video feed in real time and generates tokens on the output, it is an obvious question to ask yourself, can I apply this to robotics by letting the tokens trigger actions on a robot driver, for example? And so we have similarly developed a data set called Clever Skills that is currently under review as well, where we study this and we look at how do models perform when the job is not to instruct somebody to do a certain task, but if you instruct, quote unquote, a robot, send commands to them. And this was in the Maniskill framework, a simulation environment to study this question. Okay, so I'm going to wrap up here. A lot of this work is inspired by Edge AI, so getting capabilities of neural networks onto device. And what I focused on specifically is an emerging use case for such an ability. And the use case is on-device real-time assistance, such that you can take your model, let it look at you or listen to you, and know what to do in response to that perceptual input that comes from you through camera or microphone in real time. Here are a few pointers to how to connect with us. There's some information on data sets and model and the open source models we released and so on in the materials as well. And I'm going to answer any questions that you may have. Thank you so much for staying with me through this.
Thank you, Roland, for the presentation. As a reminder, if you have questions in the material, please submit them using the Q&A feature of the On24 interface. We've already received quite a lot of questions, so I'd like to start off with one of them. I believe that the demo that you showed us has the inference happening entirely on the edge, correct?
So it depends on what you mean by edge. So the demo I showed is, you're probably referring to the video clip I showed over here. Yes. That is running at the edge, in the sense that it's not a cloud server that is delivering the results. But this demo is an excerpt, frame grab, essentially, from a desktop that is running this system. when you run this on device, which we have done for various iterations of this model in the past, then you have to pay attention to battery life and efficiency and these kind of things. And so that is usually one step behind those frontier models that we're building. So we're currently building them out, like this particular model on a desktop machine, seeing how it behaves in real time. And then as soon as it's time to demo it, it's going to be ported to device. And there's obvious efforts. You need to have the right operators and so on. But this will be shown as an on-device demo once it's time to actually demo it. As I said, this is hot off the press. So this is really, the models are cooking as we speak, essentially, and learning and so on. And yeah, so I hope that answers your question.
Yes, thank you. Could there also be cloud or hybrid solutions for this kind of use case?
For sure, for sure. So it can make sense to have parts of the workloads happen in the cloud. And even in our very early explorations on the more clunky component-wise models that I mentioned at the beginning, even back then, we had an app in the various app stores out there, and we explored ways to do hybrid inference where some processing happens at the edge, some processing happens in the cloud, and you have batch processing and so on in the cloud. So it's obviously possible to have this split in some way, but it's interesting to note that for privacy, latency reasons foremost, but also simply for the fact that the camera is here in your home while you're doing your exercise and pixels are coming up here, there's always going to be an edge component to this whole story. So there's always going to be some processing at the edge necessary, period. That's where the pixels arise in real time. And now it's a question of scalability, privacy, latency, and so on, of how much processing should be at the edge and how much should potentially be offloaded to a cloud server that then maybe just receives features or so. The earlier demos that we were already ported to run on device in real time and so on, they are all running purely on device though. So one of the ways that we usually showcase that is by turning off Wi-Fi and then just showing, look, this model can coach you, but it's not connected to the internet.
Right. I see quite a few questions coming in related to the data sets that you mentioned. Is this data open source?
Yes, this data is open source. It is actually very, very fresh. So this whole research effort happened only very recently, at least in this particular form, using end-to-end training and so on. There are links to the various files where the data is located in the materials associated with this webinar. There will be a website showing this, which just happens not to be visible right now. So you have to really go through the deep links and get those files directly because of a migration that's happening on that website. So this will be a website accessible through the web if you just search for it. But right now, what you have to do is click on those zip files one by one and download the data that way.
Yes. And also, I think you've mentioned it before. Please check out the quick GitHub center. We have the link already listed in the resources for today's session. All right, an interesting question came in. How does sorry, I'm just gonna. I have to scroll. So can the model tell if the camera position is not suitable to get the proper input?
Interesting, yeah. It can, and it's actually interesting to note that such edge cases were part of campaigns that we did early to collect that training data. That includes that, so how visible is the user? And we have labels for that. I'm not sure if they made their way into this particular data set or not. But there's a lot of these extra labels. Is somebody taking a break? Is somebody drinking? I also already talked about is somebody disappearing from the field of view and so on. So that is there, and it enables the model to behave sensibly even when you're deviating from the expected path. You're supposed to exercise and get coaching advice, but what if you don't follow through and you do something completely different? Maybe, so what should the model do? And it's interesting to note that, I alluded to that in this little demo video that I showed. The model is actually able to pick up on the right behaviors, but it needs to be labeled. So the long form videos need to be able to tell the model, what should you say when X, Y, Z happens, like when the user walks away or something like that. Yeah, I think I'm gonna leave it at that. So there are various classes such as those. Some of them are related to even still image information. Is how many people are there, what are they doing, and so on and so forth. Maybe one thing worth noting when I was talking about that emerging media trend around humanoids and so on, it is worth pointing out that, at least as far as I can tell, no humanoid robot that is visibly currently showcased in various forums and so on, is actually able at the moment to behave sensibly and show some kind of social competence in that way, in the sense that they would understand that the user just walked away. And so what should you do when there's no more user there and I was just interacting with them? So these kind of social competencies and common sense understanding of the world around you, that's what's beautifully summarized in this word situated, that the academic community has been interested for many decades now. And so I think a good part of that, I think it's fair to say, is captured in this data set that we released, so that this kind of stuff can be studied as well.
Yeah. Speaking of the need for labeled data, I have, as a personal curiosity of mine, what about synthetic data? How would that support this line of work?
Yeah, so that's a very interesting question. So we also wondered about that when we started to embark on these kind of experiments many years ago, and then repeatedly found ourselves that we didn't care what the data is going to look like as long as it's able to train the model. And we repeatedly found at that time, and have been revisiting it a few times, that synthetic data wasn't up for the job yet, because having a system generate the subtle real-world appearance mistakes, for example, that you would do while you're working out, wasn't just quite there. And in some curious feedback loop, you could imagine that having such data, like the one that we generated for these human movements, could enable us to get better at generating synthetic data, because now we know what it means to have your, I'm using this example, your knees too far apart as you do a squat or whatever it is. So there may be a way that there could be a encouraging feedback loop between synthetic and real-world data. But when it comes to most efficiently collect that data to train a neural net, what we ended up is opting for real-world because we just couldn't get synthetic data to solve the problem for us. So anyway, I think this field is going to evolve, and that feedback loop is probably going to play out over the next years. And so it's going to be interesting to see at what point and in what way is going to synthetic data really provide a benefit over real-world data.
Yeah. So it remains to be seen. We got a few questions actually on this particular aspect. You mentioned the fitness coaching as the application here, but what other applications are you envisioning for this?
Yeah, and that's actually a broader question that the community has been asking themselves too. So the current research efforts that we are aware of that goes in the same direction are on guiding you through preparing recipes, so cooking essentially, and things like home repair, repairing objects, doing simple manipulation tasks that are not obvious, but you really want a model to look over your shoulder and give you advice. Of course, you can keep broadening that set, and it's going to be interesting again how this is going to play out with data sets coming up and so on. Lots of educational things would fall into that category. So fitness coaching is a way to educate a user about how to properly move your limbs to get certain results. But of course, any kind of movement could be coached as well. And so that ranges from repairing things, dancing, behavioral things, even like educational aspects, playing with somebody putting up towers, maybe a child putting up towers and understanding that this tower just fell apart, and whatever it is. So all of these kind of things, if you imagine what a model would need to be able to do to sensibly interact with a person in the real world, all of these tasks are going to require data that instills common sense in the model. So the model needs to understand what's going on. Is the person still here? Are they looking at me? Are they confused? Are they trying to talk to me? Did the thing they were building just fall apart? Did they just make a mistake? Are they moving correctly, et cetera, et cetera? And so the way I think it's going to play out is that the models are now at a point where they are good enough. They're going to evolve further and so on, but they're good enough to really absorb long-range training data of the kind that we showcased for fitness. And now it's a question of data, proper long-range behavior data that then allows the model to get tweaked for these various use cases.
Yeah. All right. So possibly an interesting classroom assistant sometime in the future.
Indeed. In the future.
We have a question about the learning process. So how does distillation reduce errors actually in a chain of thought model? And what would stop the distilled model from learning the same mistakes as the chain of thought?
Okay. So the way I like to think about it is when we distill information that is potentially tangentially related to the downstream task into the model, we do not rely as much on a step-by-step resolution of or description of what's going on. And so when you do step-by-step reasoning with a chain of thought, then the way that the reasoning evolves at some time step t is going to very squarely depend on the way that the reasoning generated tokens at earlier time steps. And so errors can compound. So when you're dealing with a chain, and especially when you're sampling from the model, there can be little mistakes. And over time, if you do many, many steps, they can compound. In contrast, when we use distillation so that the model encodes as much as it can about the information that is encoded in those surrogate tasks into its features at any point in time, then in some sense in the back of its head, the model knows what's the deal about the situation. And when it's then trained end to end to actually solve the task at hand, which is always part of the training objective, of course, it can just extract whatever information is in that feature vector in order to make sense of the situation. So I believe it has to do with compounding of errors if you make background information explicit as tokens rather than encoding it in a distributed representation in the features of a model.
I see.
This is maybe one more thing to comment on that. This is early work, right? So this chains of thoughts themselves have not really been used much in the past, except for these occasional ventures into various multimodal scenarios that I also talked about. But they're fairly recent, and distilling them for that matter is even more recent. And it's a very, very appealing, interesting research direction in its own right. And I think over time, we're going to get more insights into those questions. As time goes on.
Yeah. I think we have time for just one more question. And this is kind of looking towards the future, other modalities. You mentioned end-to-end learning for reacting to live video. Would similar efforts make sense for speech as well?
Yes, and I only alluded to that in various places, but this effort is just video. We did use text-to-speech in order to have the system talk back to you. And so, of course, that text-to-speech can also be more merged end-to-end into the model so that you get the right prosody, you get excited language out when the user is doing well or whatever it might be. So that's an ongoing effort. We have been dabbling with that, but this model was just video in. And then obviously on the speech side, you can ask yourself the same questions. And there is a similar community effort emerging right now to bypass transcription sort of as an intermediate step, but directly have a language model understand an audio input stream and do what it has to, perhaps with surrogate tasks, to understand this real semantics and syntax, so the actual transcription information that is in the speech signal. But if it goes that route, so if it's directly feeding into a model, it of course also gets all the extra information that is missing in a transcription, such as the tone of the person, the hesitancy maybe that they might sense, and even noises and all of these kind of things. So it can say, oh, sorry, I didn't hear you. There was a noise. Can you just repeat the second half of your sentence, etc., etc. So there is these efforts underway. I think they are similarly early, as far as I can tell. But fundamentally, they seem to all come down to the same approach, which is having a blueprint of an architecture, perhaps an LLM linked to perception in some way, which is able to be trained end-to-end on long-range data so that we can essentially do behavior cloning in that model. I think that's the key requirement and the way to solve these kind of problems.
Right. So other things to be looking forward to. Thank you very much, Roland, for your presentation today, and thank you everyone for attending. I invite you to check out the resources of today's session, the links, the papers, as well as the link to the slide deck of today's presentation. And our recording will be available on demand. Yes. Thank you very much again. Have a nice rest of your day.
Thank you, everybody.